classical particle diffusivity is pathetically small anyway. Okay, so this is the quasi-linear diffusion. It is a simple classic idea. Now, what is the fundamental idea of a diffusion? What do we describe with diffusions?
Flux uniform density gradient.
Okay, but I mean just more, it's a random walk. It's a flux produced by a random walk in a system with a gradient, right? That's the basic, in a general sense of, right, a random walk, and I should say with near Gaussian statistics, which is, you know, is there any reason why the statistics in drift wave turbulence or any other turbulence should be near Gaussian? Well, absolutely not. But we're assuming this is a kind of weakly nonlinear. This is quasi-linear theory, you know, quasi-linear is an assumption of weak nonlinearity. How weak is weak we'll come back to, okay? So it is a random walk plus a system with a kind of a mean gradient, right? And the mean gradient is equal to our friend dn dr, right? Right. So there are a number. First of all, the diffusivity has implicit in it some notion of a step squared divided by a step time, right? Or equivalently, we could, instead of a length squared over a time, it may be more convenient to write this as a velocity squared times a time, which becomes kind of a velocity times a length, right? The other thing that's important in for this to make any sense is that the diffusion length has to be less than the mean gradient. In other words, the step has to be small relative to the scale over which the mean is changing, right? So that means that L effective has to be less than L sub n, right? That's sort of essential for a diffusive picture to be valid. So, and we know from tokamak experiments, going back to the first page, right? We know from, what do we know about D, roughly? In terms of its scaling. Remember day number 1? Bone to gyrobone, and actually closer to gyrobone. Right, so it's really, we know that D goes as D bone times rho star to the alpha. What's rho star? Rho star? Omega star is the diamagnetic velocity. What's rho star? Rho star is the normalized gyro radius. Rho star equals rho over some perpendicular length scale. So in this problem, it would be rho s, you know, over L sub n, right? Okay, so that's the ratio of the gyro scale to the relevant perpendicular scale. In this simple model, the relevant perpendicular scale is just the density gradient scale length, right? So, and we know that alpha is between 0 and 1, but it's closer to 1. So we'll give, since we want to keep our jobs and build either, we'll say alpha is 1 and we'll call it gyro bone for simple terms. So, okay. All right. So we have that knowledge in the mind now. So,
Skinner,
yeah.
what do we call rho as? What do we call rho as?
It's the gyro radius with the electron temperature, sometimes called the sound radius. At the level of this, at the level of doing a careful calculation of the growth rate, you call it the gyro radius with TE. At the level of this, you don't worry, unless you're concerned with, TI over TE corrections or something. You don't care about the distinction of rho S and rho I. Call it the same thing. Okay. This is not the turbulence theorist discussion. This is the working man's discussion we're in now. How would you make a practical estimate? Right? So how do you go from this, right? This is this is the result of quasi-linear theory, right? This is directly analogous to something you do in statistical mechanics for phase transitions, invented in the former Soviet Union. What is it? Mean field theory, right? This is quasi-linear theory is mean field theory. Right, so, and it's essentially the same type of thinking as in Ginsburg-Landau, applied to, or I guess there's another fancy name, Ornstein-Zernike. But the point is not to impress you with fancy names, is to say what it is. It's a kind of mean field theory. So that's the mean field diffusivity. How do you go from this nice mean field theory calculation to something practical, to design a machine, right? In particular, suppose after you graduate from Dada, you're working in ASIPP, and Professor Lee Jong-gan comes to you and says, what's the diffusivity, right? This is the kind of realistic question that we face in the fusion program, okay? My boss in Korea comes and asks me questions like that, so another Lee. So, how do you answer that question? Now, for that kind of question, you don't have the luxury of saying, oh, excuse me, I need 2 years to go off and do a deep and profound turbulence theory. If you want to keep your job, you better come up with at least an estimate and some physical idea behind the estimate fairly fast. Okay? How do you do it? All right? Well, we already talked about this. Clearly, you have to say something about V radial, right? So, in other words, to connect the quasi-linear theory with what I would call the Bohm. It's good you say Bohm sometimes, because everyone thinks it's gyro Bohm and it's really in between. Okay, so I'll call it Bohm gyro Bohm scaling. How do you get, from here to here, and in some sense, at the level of an estimate? Suppose they could ask you, they say to you, and again, we don't have time for you to have your fun with fundamental theory, right? You tell us what we need to measure, right, to decide what this exponent is, right? In other words, what measurements are needed to resolve the scaling? and I'll say fluctuation measurements. Okay? How would you approach that question?
Fusion level.
Fluctuate, yeah, but okay, good. What else? Level is important, but I mean, really good point, but in some sense, the critical issue in this question is scale, as we shall see. Right? I mean, what is the essence, you know, just to review the other day, what is the essence of the Bohm and Gyro-Bohm business, right? I mean, we said basically we could write the diffusion, we argued on the basis of drift wave theory that we could write the diffusion as a velocity times a length scale. And now we know that velocity, probably a good guess, an upper bound on that velocity is v star, and then the length scale. And we said the length scale, if it's of order A, or maybe say L sub n here, this is Bohm. If it's of scales as the gyro radius, the answer is Gyro-Bohm. So yeah, I think the level is important, but what you want to do is you want to look at the scalings of E phi over T, and you also want to look at the scalings of, you know, the, I don't know, the kind of, how to say it, correlation length. So let's talk now in a little more detail here. Everybody get the idea here. The question is, how do we, you know, how do we get from this nice theoretical game to something practical, right? And then the other thing is, where are the hidden assumptions? So if you realize that it isn't working, how would you clean up the mess before you get fired, okay? I hope nobody circulates the tape from this.
So we can get another length scale by this fusion.
Well, how would you get a length scale out of that?
I mean, do you mean if we can get another length scale from the quadrilinear theory? Then
No,
we
you
can-
can't. Unfortunately, you can't. You'd have to do a measurement. I mean, ultimately, what you're going to need to make some sense out of this is some estimate of a length scale associated with the fluctuations, right? You know, we'll get there, but since you're getting the point. Remember when we did the mixing length estimate, remember that the first day? Right, this was 1 over k radial ln, so this is some effective length scale for the fluctuations divided by L sub n. So you'd have to do, at the level, you'd either have to do some more theory or do a simulation or do a measurement to see what that length scale is. But the scaling of that length scale is what determines the difference between Gyro-Bohm and Bohm. If L effective scales as rho I to the first power, you get Gyro-Bohm, right? That's this over here, right? If L effective is independent of rho I, you get Bohm. And if it's somewhere, and that's our friend over here. There are only 2 length scales in the problem. So if it's independent of rho I, it has to be L sub n, right? Now there are some subtleties in this that will, this is basically the question that when we talked in earlier, this is the question of what is the mixing length. And there's more, this is the simplest level discussion of this. And there's more to this story than just what I'm telling you now, but how do I say it? You begin the story at the beginning, and we'll talk about the corrections later. So, all right. All right, so now I think I can erase this and I can erase this now. So how do we make some progress here? Well, I mean, you realize at the level of an estimate, this D turbulent thing, you know, you can write this as V radial squared, right, times what I would call a correlation time, right? And you immediately know from this the correlation time would go as 1 over K parallel squared D parallel. And what is a typical value in a tokamak for K parallel? And again, if you were trapped on a desert island, you'd have to think. You know, 1 over QR, so it's basically 1 over D parallel over RQ squared, right? Okay, now how would you estimate, you know, our friend V radial? Right, there's one way that I've already told you is you could realize that this is K theta rho s CS squared. Call this 1, which is an assumption, and then there's an E phi over T squared. All right, and you could say that for drift waves, E phi over T is of order n tilde over n. And you know from the mixing length estimate that the n tilde over n is 1 over K radial L sub n. Now that's, I don't know, I think there's a cleverer way to say it. What? There's a physical argument, again. Right, a physical argument. We'll talk more about the underpinnings of this tomorrow. For kind of an upper bound on the fluctuating theta velocity, right? What do you think that physical argument is? What's the difference between V radial and V theta? One's K theta, one's KR. The other thing is the wave, the basic drift wave, right? Right, omega is equal to omega star over 1 plus K perp squared rho s squared. So it's equal to V star K theta over 1 plus K perp squared rho s squared. So the basic drift wave, no matter what this is doing, is always rotating in the toroidal direction, right? It's a fundamental idea, right? So, for, you know, one limit on this is wave breaking, right? In other words, for the drift wave to have any identity as a wave, you would kind of expect that the fluctuating theta velocity has to be less than or equal to the diamagnetic velocity, right? If it goes above the diamagnetic velocity, that says the particles supporting the drift waves are going around faster than the wave. At that point, any discussion of the wave makes no sense, right? So this then, remember, this is what gives us the idea that, you know, a kind of good estimate
I emphasize this is an estimate for saturation, is V theta tilde on the order of V star. Right? And you also know that V theta tilde is of order, oh, let's see, KR over K theta times V radial tilde. That's not me. Somebody turn off there. Thank you. The chalk situation is right? So, this immediately tells us that the radial velocity we can write as k theta over kr times, as a good estimate, as v star. Right? So that in a sense gets to the same place as this argument, but is a bit more physical, I think. I mean, this is just a kind of wave-breaking limit. Okay. Right, so, our diffusivity then goes as something like k theta squared over kr squared times v star squared, okay, over, our friend k parallel squared d parallel. Now, so this is starting to be, an interesting little estimate. You notice, what is the basic scaling of this? This goes as k theta squared over kr squared. V star is rho s squared c sub s squared over L sub n squared times k parallel squared d parallel. Okay? And let me, I'm going to have to erase this. Right, so that's a kind of basic. This is an example of a mixing estimate. Mixing or wave breaking, whatever you want to call it, right? This is how you get, a kind of a handle on this thing. Now, so you notice that our estimated diffusivity squared times rho s squared cs over L sub n squared, and where's my other friend, k parallel squared d parallel. Okay, there we go. So let's see how we break this out. This goes as k theta over k radial quantity squared. And you notice I can write this as rho s cs, right, which is the bone. And then I can take the other factor of rho s over ln, and I have this, right? So what's that? That's d gyro bone, isn't it, right? And then I have c sub s over L sub n over k parallel squared d, and I remember for k parallel I put d parallel over r cubed quantity squared.
Well, you notice this is now, starting to look interesting. This is d gyro bone, isn't it? Right? Right? This is effectively a dimensionless ratio. And this has no rho star dependence. And this is less than 1 because you realize this is basically omega star over the parallel diffusion range, which by definition is less than 1 in this limit. So really, the estimated diffusion coefficient, with one assumption, is something like this times d gyro bone times what I don't know, I'm going to call this sigma, something to do with tau. It's a dimensionless ratio involving time. So the answer, this is the answer, that the key issue is anisotropy of the eddies. Right, so if k theta is of order kr squared, then you could argue that an upper bound, a wave-breaking estimate of the diffusivity is essentially gyro bone scaling. If, however, kr is much less than k theta, this might suggest that you could go toward bone, depending on what kr is. So what I would say to my boss is, it's probably will be gyro bone scaling, but you better measure the structure of the spectrum and look at the deviations from isotropy. If it's strongly anisotropic, then the scaling will not be so favorable. And in particular, it's kind of crucial to estimate the rho star scale, to look at the rho star scaling of the anisotropy. Right, that's the simple-minded estimate.
But from the spectrum, how can I know what is K0 and what is KR?
From a spectrum?
Yeah.
Well, you have a probe array, so you can basically have radially displaced probes and look at the KR structure, and you can have colloidally displaced probes and look at the theta structure. Right? It's a two-dimensional spectrum in KR and K theta. And the way
You look at the fluctuation spectrum.
yeah.
Then how can you estimate the mean? Do you mean some kind of mean? K0 is some kind of mean
Well, once if you
weighted by the energy?
exactly. If you have a measurement of phi of KR and K theta
Yeah.
squared, then you can immediately look at, say dk theta dkr times kr squared, what am I looking at here? K theta squared over kr squared times phi of kr k theta. Right, and that's effectively an energy, and then if you want to normalize it, you'd write integral dk theta dkr times phi squared. So it's a weighted average, right? That defines what, in turbulence language, you're basically asking is you want to know the integral scale,
Yeah.
both in theta and radius.
Okay, so you're 1 over integral scale.
Yeah, exactly. But it's it's the ratio of integral scales.
Yeah, ratio of
It's the ratio of integral
integral
scales.
scales.
Yeah. And there's something coming later in the lecture series that helps that to be close to 1, namely the zonal flow helps with that. But we'll get there. It's coming. But this is the classic estimate, right? And this is in other words, drift wave turbulence with isotropic structure naturally leads to essentially gyro bone scalings. With anisotropic structure, it can deviate from gyro bone. The origin of the simple estimate is quasi-linear theory and some kind of simple model of wave breaking or mixing. This, hence the name mixing length estimate. It is not rigorous, however, it is not too bad either. In other words, as I've said many times, the measured diffusivity scaling is, you know, it's closer to gyro bone than bone, so it's not doing too bad. Okay, and it's a, you know, it's a basic fundamental idea.
I have a question. In this equation,
Which one, this one?
Yeah, the diffusivity
Right.
is of course the function of fluctuation level.
Right.
But you replace the level as the wave breaking.
Estimate, yeah.
Yeah,
exactly.
but I think the transport will of course affect the saturation level.
Of course, well, I mean, you have, in a theory or a simulation, you determine the saturation level, okay? So what I'm saying is in some sense, this is a kind of upper limit on how big the fluctuations can be and still fall in the realm of drift wave theory, okay? Obviously, I mean, there's a, you know, maybe I don't understand your question. Try.
I want to say if we use another limit to estimate VR,
Yeah.
then we may get another.
Of course,
solution.
of course, of course.
Yep, and you say this is much closer to gerbil, but you use an upper limit of velocity. So I mean
Yeah, but
the fluctuation level may be not that high. It may be very low.
But if the fluctuation level is lower, it's hard to see how the fluctuation level can be low and the radial scale be big. Think it right. In other words, the whole idea here is in this, you know, n tilde over n is of order 1 over kr L sub n is of order the effective scale over L sub n. So it's hard to see how this can be big, right, and this be small. See what I mean? That's the essential idea here.
The higher fluctuation level means it must have smaller.
Higher fluctuation would mean bigger cell. Lower kr, bigger radial scale, typically.
But it's not linear relation, but it's the relation between amplitude and the scale.
I mean, this is not a linear relation. This is essentially a kind of it's an estimate derived from balancing what amounts to the linear wave frequency with the nonlinear decorrelation rate, right? So it's basically saying that what is the biggest fluctuation level you can have and still make contact with the linear wave theory. That's what it's asking. And nobody says, by the way, if it's smaller, that's good, right? I mean, you know, that means you get less transport, okay?
But usually it should be larger, like turbulence.
Well, but remember, sir, you weren't here in day one. Remember, you know, the kind of, when you look at the measurements of frequency spectra at fixed K, the line width of fixed K is roughly of order the frequency. So it says it's not really strong turbulence. Right? In other words, it's kind of on the margin between, that's where this idea comes from. It's kind of on the margin between weak and strong. Right?
You mean that you might mean the line scale?
Exactly, exactly.
mean
The type of thinking that goes into this is exactly, ultimately, the same thinking as the Rhine scale.
So most of the fluctuation are at that scale.
Or something like that,
Somehow.
yes, something like that, yes. Well, that's a characteristic scale, but I mean, the turbulence, that's something that is very clear
in both the experiments and the simulations, the turbulence is not the same as high Reynolds number fluid
So
turbulence.
it's kind of weak.
Well, it's weak or marginal. In other words, what makes it
There's a
hard,
lot of
if it
ways.
were weak, we could just do weak turbulence theory, and
Not
this
very
room
weak.
would be lit by fusion power, okay? Unfortunately, it's kind of on the boundary between weak and strong.
Okay.
That's what makes it hard.
Yeah. I guess you need a break.
Yeah, I think it's time for a break, yes.
The call is for your break.
What?
I just got a call.
Okay, have a break.
That's for your break.
All right, good, thank you.
Okay.
Well, I need it. So we'll have like a 15, 20-minute break. I need a rest. I'll be back.
Yeah, I